Greetings everyone. Welcome back to Intermediate Algebra. It's time to get into the serious topics that are going to be useful in all of the math subjects that you take after this. Factoring is something that comes up everywhere in mathematics, and this is where we start. Greatest common factor, GCF. You'll hear that one a lot. So let's start with numbers, build into letters, and then mix both of them together. The greatest common factor is whenever you can take factors that are in common. So let's break down those words and what they mean, right? Factor, don't forget, factor means to unmultiply. And you might think, well, Professor Simon, is that division then? Not exactly. Unmultiplying just simply means undoing the multiplication. Now, sometimes you can use division to help you with that idea, but when you want to factor something, you're breaking it up into what we call factors. So, for example, 6 is equal to 2 times 3. 6 is what I started with. 2 times 3 is what I factored it into. Notice I didn't actually write a division, right? Then 2 and 3 are the factors of 6, okay? So each one of these is a factor. And I have factored the 6, okay? So the factor is a noun, to factor is also a verb. So the greatest common factor means I'm going to break these down with factoring, and then I'm going to find the common pieces, the common factors. Okay? So 45 and 75. 45 is 5 times 9. But 9 can be broken down more. We want to go down as low as we can to prime factors. So I'd actually write 5 times 3 times 3. Okay? This is the factorization of 45, the prime factorization. 75 is going to be 25 times 3. But I can break 25 down further. So I have 5 times 5 times 3. Now the reason I like writing these things horizontally like this is because we can do the little bubble group method. I'm going to circle groups of whatever they have in common. I notice that they have a 5 in common. I notice that they have a 3 in common. So my greatest common factor, my GCF, is going to be a 5 times 3. In other words, the greatest common factor is 15. 15, in other words, is the largest number that will divide both of these values evenly. 15 goes into 45, 15 goes into 75, both of them with division, right? And it's the largest number that does it. That's why it's the greatest common, because it can divide both of them. And it's a factor because it divides both of them. Okay, next, 32. Well, 32 is 4 times 8, right? Okay, but then 4 and 8 can be broken down even more. 4 is 2 times 2. 8 is 2 times 4, so 2 times, and then 4 is another 2 times 2, right? That's 4 times 8. So that's the prime factorization for 32. 33, 3 and 11. Well, they don't have any factors in common. What does that mean? That the GCF is 1. 1 is going to be the largest number that will divide evenly into both 32 and 33. Because 1 divides into everything, right? Anything divided by 1 is itself. That's a guarantee. So if they don't have anything in common, your GCF is just the number 1, because everybody has 1 as a factor. We just don't write it. Okay, next, 14 is 2 times 7. 24 is 4 times 6, right? So 4 is 2 times 2, and 6 is 2 times 3, right? That's 4 times 6 is 24. Okay. Next, 60. 60 I can break up into 6 times 10, right? Well, 6 is 2 times 3, and 10 is 2 times 5. So there we have it. I have 6 times 10 is 60. Now, remember, we're doing the greatest common factor. So I have to circle, in this case, a group that would have the same in all 3. So I notice already that all 3 of them have a single 2, like this. Then the 14 is done, except for the 7, but nothing else has a 7. So there are no other groups from all 3 where they share something. That means that the GCF here is 2. Okay? So we can use division to help us with this, but mostly it's just finding values that will divide evenly into each one of these. And usually this grouping method where you can line everything up is the best visual way. Okay? Greatest common factor for variables. This is just a counting game, because remember, when you're multiplying variables, especially the exponents, it's really just the same letter over and over and over again. Okay? So they're going to have things in common if you even see the same letter. So look, y, and y. They're going to have those in common, right? So really it's just how many do they have in common is the better way to question this one. So let's write it out, right? I have 3 of these. I have 5 of these. And I have 8 of these. Right? Well, let's see. What do they all have in common? I see a single y, another single y, and yet another. So that means I have y times y times y for my GCF. Or in other words, y cubed. But there was an easier way to do that. Okay? Whenever you're doing the GCF for variables, you always take the lowest power that you see of that variable. Okay? GCF for variables is just take the lowest exponent. Okay? Of the ones that you see. Now, that doesn't mean that you take the lowest of all exponents that you see. They have to be in common, right? All of these y's were y's. They were in common. So y cubed, the lowest one, is the greatest common factor. 3 y's is what all of the terms could afford to pay, if you want to think of it that way. Okay? So right here in this problem, I want to look at these 3 and say what the greatest common factor is. Well, I can tell you already what the variable portion is. Look, x squared, x to the 4th, x to the 1. They're all x's, right? They have that in common. So GCF for variables, take the lowest exponent. That means in my GCF, I should expect x to the 1, okay, because this is the lowest. That means x to the 1 is part of my GCF. So I'm going to take just that. And then I can just forget about the rest of the variable portions, right? And I don't even need to worry about the negative either, because they don't all have it. But 9, however, that's 3 times 3. 15, 3 times 5, and 6 is 3 times 2. So just the number portions, I'll be taking the 3 that they have in common. So my GCF is going to be the x that I found from the lowest power and the 3 that they have in common. So my GCF is literally 3x. Okay, so remember with variables, it's just a counting game. We're finding out how many do they all share, and it's always going to be that lowest as long as all of the letters are the same. Okay, so look over here at this one. 11 is one of the numbers, 1 and 1. So the numbers don't have anything in common. 11 is prime, I can't even break it up, and none of the other ones have 11. So there's no number portion to this particular GCF. But I've got the A's in common and the B's in common, right? So I'm looking at the A's here, and I'm going to take the lowest exponent that I see. A to the 1, A to the 2, A to the 1. So I'm going to take A to the 1. And then again, I've got the B's in common, right? All of these are B's. I have B to the 3, B to the 3, B to the 2. So what's the lowest? B to the 2. Therefore, my GCF is AB squared. Okay? That's always the way that you can write out GCF in a grouping stance, or if you need to see all the steps. After you do these a few times, though, my hope for you is that eventually you'll be able to do this without having to write out all of these groupings. You should be able to look at the numbers and say, hey, I notice 3 can divide into everything, or hey, I see these variables, I'm going to take the lowest power. Eventually, you need to get to the point where you've practiced enough where you don't need to write out all of these structures, and you can just look at this and say, oh, y to the 3 is the lowest, take that out. Or over here, 45 and 75 both have a 5 and both have a 3, so it's 15. Okay? Even if you have to do it in stages, if you practice this enough, the hopes is that you won't have to write out all these structures. It's a good place to start to help you understand what's going on, but practice to eventually not have to write it out so much. Okay? Now that we've discussed how to find a GCF, let's use that skill to actually GCF factor a polynomial. What this is basically is the opposite of the distributive property that you've used in the past to simplify equations and expressions. Typically, when you've done distribution, you've taken something like 6x and you've multiplied it by both the a and b and whatever else is in the parentheses of some sort of expression where you have an addition or subtraction in parentheses. Typically, you're going in this direction. What we want to do is the opposite of that. Distribution works by giving everybody a common piece. What we're doing with greatest common factor is finding that common piece in each term, and then we're going to take it back. So you look for the common piece in here, like in this case 6x, and then I would rewrite it as that common factor piece outside of a set of parentheses, and then you're just going to write down all of the leftover parts still added in the order that you have. Okay? The main thing you have to remember is that however many terms you start with, 2 here, that's how many terms should be in your parentheses. Okay? You never gain or lose the number of terms. If I have 2 terms here, then I've got 2 terms in the parentheses. If I have 5 terms over here, then I'll have 5 terms in the parentheses. Okay? Division can sometimes help a little bit as well. So right here, I'm going to look at 42x minus 35, and I want to factor out the greatest common factor. So I'm going to start with the easier portion, which is the letters. Right? This guy has an x. This guy doesn't have any letters. So they don't have any variables in common So that's not going to be part of my GCF, so I move on. 42 and 35. What would a common factor be of 42 and 35? Well, if you have to, over on the side, you can write down the method that we did before for breaking these things down if you wish. If it helps you, you can write down the 42 and the 35 as 2 times 3 times 7 and 5 times 7. And you can see that they have the 7 in common. 42 is 6 times 7, that's why I have 2 times 3 times 7. If it helps you to start with, but remember what I was just saying in the end of the last scene, you really want to work towards being able to do the GCF by noticing what they have in common instead of having to write out all of these steps. It's okay if you do write them out. I'm not saying it's a bad thing, but as you practice, I'm hoping that you'll see that these things will just start to come more naturally, and you'll just start saying, oh look, 7 goes into both of those numbers. I can see my division of 7 works for both of those, and so on and so on. Okay, so since 7 is the number that works for both of those, what I'm going to do is write the 7 outside of a set of parentheses, like so. Inside of this parentheses, I'm going to divide out a 7. Basically, I'm taking back, I'm undistributing the 7. So 42 divided by 7 is 6. So I have 6 times x minus 35 divided by 7 is 5. So then this rearrangement of terms is actually equal to the original. These two are equal in value, okay? But this one is considered factored now. I have factored out a greatest common factor. Next, y to the third minus y squared. So I can see there's no numbers that I need to look at here. Both of them just have a 1 in front. But they both have y's. And remember, the GCF for variables, if they have a letter in common, is always whatever the lowest exponent is. So between y to the 3 and y to the 2, the lowest power I see is y to the 2. So that's what I'm going to pull out in front of my parentheses, y squared. And I have my parentheses. Now I'm going to use division. And don't forget, when you divide powers, things with exponents, you subtract the exponents. So for example, y to the 3 divided by y to the 2 is the same thing as saying y to the 3 minus 2 power. Or in other words, y to the 1. Okay? So if you're dividing, that means I'm just going to be subtracting the powers. Remember, the exponents on these things is just a counting game. So I'm going to divide. Y to the 3 divided by y to the 2 is going to be y to the 1, or just y, minus y to the 2 divided by y to the 2. Well, that's just going to give me y to the 0 if you want to look at it one way. Or another way to look at it is I'll have y squared divided by y squared. That's something divided by itself. That means it's 1. Okay, no matter which way you look at it, it's going to be that though. If you have y squared divided by y squared and you do the 2 minus 2 and you get y to the 0, don't forget anything to the 0 power is 1 automatically. Okay? Now between these two, don't forget that you can actually check yourself just by using the distributive property. I could do 7 times 6x gives me 42x. 7 times negative 5 gives me negative 35. And it comes out to be the same thing, which means we did it correctly. Y squared times y is y cubed. Y squared times 1 is itself y squared. So we factored it out correctly. Okay, having 3 terms doesn't change anything. I can find the GCF for all 3 pieces, or even if it's 20 pieces, right? Doesn't matter. Find the thing that all of them have in common. Well, I'm looking at the letters first, right? That's easier. I'll have a cubed, a squared, and a. They all have the variable a, so I'll definitely be pulling that out. Also, I'm noticing now that I have to look at the lowest power, right? 3, 2, 1. That means I'll be pulling out a to the 1 as my lowest power. So that's what I'm going to write out front. Next, I'm going to look at the numbers, 12, 10, and 2. I need a number that will divide evenly into all of them. 12, 10, and 2, I can divide all of them by 2. Okay? Now, at this point, I also have an option. Because I see some negatives in there, sometimes you may want to factor out a negative. Okay? That's completely possible. In fact, you can always factor out a negative no matter what you have actually in your polynomial. Okay? I'm going to do one time without the negative, and I'm going to show you also factoring out with the negative. Okay? Because you can actually do that at any time you want. Even if you don't see any negatives, you can actually still factor out a negative because it's easy as just changing signs. So here at first, I'm just going to go ahead and go with it with 2a being my GCF. So I'm going to divide. 12 divided by, or negative 12 rather, divided by 2 is negative 6. A to the 3 divided by a is a squared. 10 divided by 2 is 5. A squared divided by a is a. Negative 2 divided by 2 is negative 1. And a divided by a is also 1. So I'm just going to leave it as that. Okay? So this is completely factored. But remember, I was saying we had a choice. Or I could have factored out negative 2a here. All that would do is factor a negative out of every piece. And remember, what negatives do in multiplication and division is just change signs. So if this was your choice, that's fine. All of these would just be opposite because all of my divisions would have been opposite. So this would just be 6a squared minus 5a and plus 1. Okay? Like I was saying, you can actually do that in any of these GCFs. Watch. On this one right here, if I really wanted to, I could have factored out a negative 7. Like this. And again, all that would do is reverse my signs. I would have negative 6x plus 5. Whenever you're doing a greatest common factor factoring, you can factor a negative out whenever it suits you. Okay? All it does is change the signs on everything inside of your parentheses. So really it's just more of a question of, do you need to, do you want to, is it required for what you're doing, or does it just make you feel more comfortable? In this one right here, I'm more comfortable with the one we did first because it just looks neater. But quite honestly, I'm more comfortable with factoring out the negative on this one. And it's mainly to do with the leading coefficient. A lot of times we like our front runner of the parentheses to be positive. That doesn't mean either one of these is incorrect. Both of these are completely correct as far as factoring out the GCF. It's really just a situational and an opinion of which one you like better. Okay? Let's go again. I have, let's do the variables first, right? I'm going to write out my parentheses, and I'm going to look through. I have x, x, and x. It looks like everybody has an x, so I'm going to definitely put that. I see y, y, and y, so I'm definitely going to put y. And I'm going to look for the lowest powers on each one now. X to the 1, x to the 1, x to the 1. So the lowest is 1. They're all 1, right? For y, I have 5, 4, and 3. So I'm going to take the lowest. That's going to be 3. Okay, now let's do the numbers. 27, 9, and negative 18. Well, it would seem to me that all of them are multiples of 9. I'm going to do 9 here because 9 can go into 27, 9 can go into 9, and 9 can go into 18. Okay, so now that I know that 9 can go into each one, I can do each division. 27 divided by 9 is going to give me 3. X divided by x is canceled out. Y to the 5th divided by y to the 3. 5 minus 3 gives me squared. Plus 9 divided by 9 is 1. X divided by x also 1. Y to the 4 divided by y to the 3. 4 minus 3, I have a y to the 1 power left. Minus 18 divided by 9 is 2. Right? X divided by x is 1. Y to the 3 divided by y to the 3 is also 1. So I'm done there. Again, don't forget to go back and double check by distributing. 9xy to the 3rd times 3y squared gives me 27xy to the 5th. 9xy to the 3rd times y gives me 9xy to the 4th. 9xy to the 3rd times negative 2 gives me negative 18xy cubed. Okay? Now this kind of factoring is not just for singular type of objects like these GCFs that we have. All of these GCFs that we've done so far are a single term. They have multiple little factors in it, but they're a single term because multiple terms means you have addition and things like that. Okay? It is possible to factor an entire grouping, an entire polynomial, as long as you see it in common. And that's the big thing about the C in GCF. As long as you have something that is common, it can be completely factored out. Okay? So for example, I have some groupings here, and that word's going to be important later. Groupings of this and this. X times a minus 2 minus, and then I have another grouping, 3 times a minus 2. I'm noticing that they both have this a minus 2 big chunk. Okay? Now for just a moment, I want you to pretend that what we have here is x times some value like b minus 3 times the same value. Just imagine for a second that I have x times b minus 3 times b. Wouldn't I be able to say that I can factor out the b that they have in common, much like I did the 7 over here or the y squared down here? They have this big B in common, so wouldn't I just be able to say that that's B times x minus 3, right? That's the mentality you should be looking at this polynomial with. I have that chunk, a minus 2, but it's all one chunk, and they both have it. So, since they both have the a minus 2, I write it out front, like this. And if I were to divide it out, I would be left with x minus 3 still. So that's what I have, x minus 3. And this is the final answer on that one. So you can factor large groupings like that, as long as you find it in common. So one more example. I'm looking at these two groupings and I'm noticing they both have 2m plus n, right? They both have that one chunk. So since they have it in common, I'm going to pull that out front. 2m plus n, like this, in front of a parentheses. So I just took that chunk and moved it out front. So if I were to divide it out and it were gone, notice I would be left with this minus, if I wipe this out, there's nothing left. But don't forget, GCF can't change the number of groupings. I have two big groupings, so I'd better have two terms here. Don't forget there's an understood 1 right here. Okay? So that's what I'm going to have. I'm going to have the 5x squared y cubed here, this, and then minus 1 is going to be left over there. And then that's the factored out version of that polynomial. To finish up this lecture, I want to talk about an extension of common factoring, common factor factoring. Okay? It's called factoring by grouping. And basically, it's the next step up from those last two examples that we were just discussing. What happens is, in factoring by grouping, is you start with a GCF that works only in small groups, and then hopefully that leads to some larger chunk like the ones we were just discussing that you can pull out later. And what this actually ends up being is the opposite of what some people call the FOIL method, which is multiplying two binomials. Okay? So factoring by grouping, first you got to remember a couple of things. You need at least 4 terms to begin with. You need at least 4 terms to do factoring by grouping to begin with. Okay? And once you're done factoring, if it's 4 terms, you should be expecting 2 binomials multiplied. Okay? So, from here, let me just show you what how it works. With factoring by grouping, typically you don't have to rearrange anything, although it is possible. You can rearrange some of the middle pieces and it would still work out. Typically you don't have to, though. And all the ones we're doing here, we don't have to. The groupings go like this. I'm going to take whatever 2 I can. I'm going to notice whatever 2 terms I can. I'm going to find them such that they have something in common. Some GCF, not from all pieces, okay, but just from 2 of them. And then I'll try to do the same thing with whichever other 2 were remaining. In this case, I picked the front 2 because I noticed they both have x's. In fact, they both have x squares, right? Because squared is the lowest power of these 2. And I also noticed that they both will divide by 7. So that's what, if that's what they are brought together, that's what's making them a group. That's also what I'm going to factor out, 7x squared. So then I go ahead and do that. 28 divided by 7 is 4. 3 minus 2 is 1. Negative 7 divided by 7 is negative 1. 2 minus 2 is gone. When you're factoring by grouping, always take whatever this middle sign is and match it. Okay? When it's a positive, it doesn't really do that much different. But when this is a negative and you match it, it's telling you that you need to factor a negative out of the next grouping. Remember how I said you can do a negative whenever you need to or whenever it seems convenient? This is when you need to make that choice for this particular method. Sometimes you may have to factor out a negative just so that you can do this match. Okay, but whatever that is, you're going to want to match it. And now between 12 and 3, what they have in common is a 3. 12x divided by 3 is 4x, and negative 3 divided by 3 is negative 1. At this point, you're hoping to see 2 chunks, 2 large groupings that are the same. In this case, the 4x minus 1 and the 4x minus 1. Well, just like in the last one, I can take that they have in common and pull it out. Right? I'm going to divide it to the outside, leaving me with the 7x squared plus 3. And now it is complete. That is factored version of this 4-term polynomial. Okay? Let's start going through all the rest of examples. It's going to be the same thing. I'm going to try to grab the front 2 and the back 2 every time. So 2xy plus 5y squared. I'm going to look at these 2 and see what do they have in common. Well, the 2 and the 5 have nothing in common. This guy has an x, this guy doesn't. But they both have y's, don't they? Okay, so y. And if I divide y by y, it's gone, but I'm still left with a 2x. Here, plus 5 divided by 1 is 5. And y squared divided by y, I'll just do 2 minus 1 is 1y left over. Here's that middle sign. I'm going to match it with a negative. And what that's telling me is I need to factor a negative out of this grouping. Between 4 and 10, they both have a 2. This one has x, this one has y, so there's no variables in common. If I do negative 4 divide by negative 2, I get 2x. And negative 10 divide by negative 2, I get 5 times y. Lo and behold, look, 2x plus 5y, 2x plus 5y. They have the big chunk in common. So I'm going to take that and divide it out front. 2x plus 5y. And what am I left with? The y minus 2. If you're looking for a way to check yourself on these, don't forget that this is the opposite of polynomial multiplication that some people like to call FOIL. So I'll be multiplying the 2x times the y. That will give me this. 2x times negative 2. That will give me this. 5y times y will give me the 5y squared. And 5y times negative 2 will give me the negative 10y. So this is the correct factorization, right? The unmultiplication. Remember, that's what factoring means, to unmultiply. So I have unmultiplied these two binomials that used to be what made up this. Okay, let's go again. Let's take the front two. These two guys have a z in common, leaving me with 3z plus 4w. Match the middle sign, plus. These guys have nothing in common. 3z, 4w, and that's okay. 3z plus 4w, I'm going to write it as a group, and since they had nothing else in common, I'm just going to remind myself that there's a 1 in front of there. Okay? Notice my grouping is matched, 3z plus 4w, so I'm going to pull that out front, and I'm going to be left with z plus 1. Okay? Now, factoring by grouping doesn't have to work. Some things just may not be factorable. Factoring doesn't have to always be present. For example, let's look at this one. I notice these two have an 8 in common, so I pull that out. Match the middle sign, plus. I notice these two guys have x's in common, and I take the lower power squared. 3 minus 2 leaves me with an x. Minus 5, 2 minus 2, all the x's are gone in that sense. And I'm noticing now this one has x minus 1 and this one has x minus 5. No good. Okay? Not factorable by grouping. Probably not factorable at all, which, if you're going to say not factorable, the actual word is prime. Okay? You got to be careful with that word prime, though, as a final answer. If you say prime, that means that whatever they handed you at the very beginning is what you're handing right back to them. If you were able to take a GCF out of everything and then you were moving on to this other method, sometimes that's what happens. We'll work through a couple of different factoring methods in some of the bigger problems. You can't say prime if you even did a little bit of factoring. Okay? We weren't able to do any, so we would answer prime. Okay? But keep in mind, prime is a very, very strict word that nothing could be done from the very beginning. Okay, let's do this one. 3xy minus 4. They have nothing in common. And x minus 12y. Those also have nothing in common. Well, that doesn't mean automatically that my grouping is going to fail. It probably means I need to move some stuff around and try to make this work a little bit better. So let's do this. Let's put together some things that do have some things in common. For example, what if I swap these two terms here? it would look like this. 3xy plus x minus 4 minus 12y. Now I see these two guys have an x in common, and these two guys have at least a 4 and a negative in common. Well, this might just work out then, won't it? Let's see. If I factor the x out of these two, x times 3y plus 1, don't forget the plus 1 because x divided by x is 1. Match the middle sign, negative. 4 and 12 have a 4 in common. Negative 4 divided by negative 4 is 1. Negative 12 divided by negative 4 is positive 3 and a y. Don't forget that that's important. The fact that I chose to match that negative means I was factoring it out, and your divisions should come out appropriately. Negative divided by negative is positive. Negative divided by negative is also positive. That's important. Okay, they look slightly different, but remember, adding has that commutative property. You can add things in any order and it's the same thing. So 3y plus 1 and 1 plus 3y are actually the same binomial, just written in an opposite order. So it's okay to go ahead and factor those out. I can factor out the large grouping 3y plus 1, and I'll be left with x minus 4. Okay? So we did have to rearrange them. Like I said, it's rare, but it does happen. You sometimes have to put things in a proper grouping, and you want to make sure you're choosing your groups by something that they have in common. Okay? And then typically it will work out as long as you can get that large chunk to be the same. One more. 15xy, 15ay. Those two seem to have something in common. Negative 3xa, negative 3a squared. Those two also seem to have something in common. Okay? So let's go through that one. Let's see. Let's do 15y right here. And let's say that it's times, because I'm taking the 15y out, I'm going to have x plus, and I took the 15y out, so it has a, right? Match the middle sign, negative. I notice both of these have a 3, and I notice they both have an a also. I'm picking a to the 1 because it's the lower of the two a powers. And if I take negative 3 divided by negative 3, that's 1. A divided by a is also 1. I'm left with 1x though. Negative 3 divided by negative 3 is going to be plus 1. A squared divided by a is going to give me a. Both of these have x plus a, so I pull that out, leaving me with 15y minus 3 in the other parentheses, right? Because the x plus a is common. I'm left with the 15y minus, whoops, messed up there, minus 3a. I hope that this lecture has helped you see how we use common factors in these types of groupings and in these types of factoring processes. The most important and the most used factoring process is the GCF factoring process. Next, after that, we do a lot of sub-applications like grouping with the GCF factoring. So you need to get good at GCF factoring. And then after this, move on to the more advanced factoring methods like trinomials and special products and difference of squares and things like that.